So we'll just start with this very basic definition. Uh, so I have just written out the first line. So let m be a fixed integer, if a positive integer at least one. Two integers x and y are said to be congruent modulo m if m divides the difference. So this sign stands for divides. So if m divides the difference. So uh, this very simple thing has many use. So let's just start with one. So which you already know. So let x be an integer, which we write the decimal expansion at as this. So xn x min minus 1 to x naught 10. So just 10. This 10 just refers to the base. So this is the decimal expansion. Decimal expansion. And so what does it mean? This is x to the xn 10 to the n plus x n minus 1 10 to the n minus 1 and so on, x1 10 plus x naught. So of course x1 to x naught are integers between 0 and 9. So just observe that 10 to the n, you can write it as 9 plus 1 power n. Okay, my brackets are rather poor. So 10, 1, 9 plus 1 to the n. And if you expand it by binomial theorem, then what you can say is that this is 1 modulo 9. Because everything else in the expansion would be divisible by 9. So you would be left with the last one, which is 1. So it's 1 mod 9. So if we use this, then what we get is x is congruent to the digit sum, the sum of its digits. So every integer is congruent to sum of its digits modulo 9. So this is mod 9. And this can be used to check long calculations, especially long multiplications. You can check if it is correct or not. Of course, if it is equal, that doesn't mean it's correct. But if it is not equal, if the integer is not equal to the digit sum modulo 9, then of course the calculation is wrong. So just to give an example, I would give a small exercise. So yeah, so let me just recall the numbers correctly. So check this multiplication. So check the multiplication. So this is just to amuse yourself. So into 40162. Of course, so this is to be checked without multiplying using the trick. So this is equal to 233 256 846. Yeah, so just use this trick to check if this calculation is correct. So it's already very useful. So that is what I wanted to emphasize, that it's a very simple notion, but it's useful. Just to get used to this reducing modulo some integer, I would also mention a couple of exercises, but maybe I'll just put it when I send the file. So just not to waste too much of time now. So I would just go to a formal definition which I have already written down. So yeah, my live handwriting is bad, so I'm just trying to do that. And so I wrote few lines. So modulo m, so by modulo m, so two integers are congruent modulo m if their difference is divisible by m. M is a positive integer, at least one. So modulo m, so this relation is an equivalence relation. So it is reflexive, transitive, and symmetric. And the set of equivalence classes, as you know, are denoted by z of m, z subscript m. And all the equivalence classes can be written like this. So that's one of the way to write it. So we write x in bracket and put an m to emphasize that it is an equivalence class. So it's an equivalence class which contains this integer x. And addition and multiplication are defined like this. So I just put a slightly different sign for addition just to make sure that just to differentiate it from ordinary addition and ordinary multiplication. So this is my addition of these two equivalence classes, and here also the same. So they are defined. So if one class is represented by x and another y, then the sum of them is represented by x plus y, and here also xy. So Zm in that way, the set of all equivalence classes can be written like this. So these are all all these are just to make sure that we are using same notations. So it's essentially to uh, standardize the notations for these lectures. So we write 0 m, 1 m, and this m minus 1 m. So it's a set with m minus 1 elements, m elements, sorry. It's a set with m elements. And it has two binary operation, which we are calling addition and multiplication. And with those two operations, it's a commutative ring. So in practice, we don't write this clumsy notation. That would be too difficult to write all the time, and so instead of that, we just use just the integer representatives. So we just use 0 1 to m minus 1, keeping in mind that they are not really the integers but the equivalence classes. So for throughout the lecture, we would use that. Would not write it with these brackets and all this. That's very cumbersome. So now, just to again to get used to this kind of arithmetic. So it'd be nice to solve these linear equations in two variables. So which we usually do in real numbers, integers. So here it is to be done modulo 7 and modulo 5. And it is a quadratic equation in so you can solve it in Z11. Of course, you can try in other ZMs. So this is so these are two things to try. Yeah, so I would probably write out little more, some more exercises when I send it. So I would keep this page also some space in this page and go to the next one. Mm, yeah. So just to mention it again that this is a commutative ring. So for under addition we have inverses, but for multiplication not everyone may have inverses. So the next thing is to look at the inverse. So what are the invertible elements? So first of all, what do I mean by invertible element? So an element R in Zm is said to be invertible if there exists another element such that the product of R and X is congruent to 1 modulo M. So yeah, so we were writing congruent with three equalities, so equivalent sort of thing. So let's keep that. Yeah. So Rx, this product of these two integers is congruent to 1 modulo M. And if that happens, then we write x as r inverse, so inverse of r. So this is just a notation to denote the inverse of r. So our first theorem is an element is invertible if and only if, so an element R is invertible in Zm if and only if R and M are relatively co-prime. So this is the notation for GCD. So GCD is 1. So let's prove that. So, by the way, if anything is unclear, please feel free to stop me at any point of time. So, and ask questions. So, if you have any question at all, ask it. So, I mean that's for the entire lecture. Whenever you have question, please interrupt and ask. So, and more for the tutorials, of course. Tutorials should be very interactive. Even lectures should be interactive. So, let's try to prove this. So suppose R is invertible. So we go one way. So suppose R in Zm is invertible. Then there exists an X in Zm such that, so here one thing we are doing, we are just identifying an equivalence class and its representative. So equivalence classes are all represented by integers and we are identifying. So there is no harm in doing that. So that we know. So because any representative will give you the same thing modulo n. So there exists an X such that Rx is equivalent to 1 mod M. That's just the definition of just this about definition of invertible element. X being the inverse. So that, so what does this relation mean? This is going to mean that Rx minus 1 is a multiple of M. So that should be some My for some y in Z. So so these two are congruent. So Rx and 1 are congruent modulo M. That means that the difference is divisible by M. So difference is a multiple of M. So R, yeah, and that's good enough. So this implies that R and M has to have GCD 1. Because if the GCD is not 1, then you have an integer. So if the GCD is suppose D, so then you have an D greater than 1, then you have an integer greater than 1 which divides this as well as this. So it is going to divide 1, which is not possible. So it has to be 1. So that gives one way. And the other way, so next, let the GCD is 1. So suppose the GCD is 1. Then there exists.
Sir, please clear the above line.
So which one?
TD
The
for
GCD?
attention.
GCD?
Yeah,
Yeah,
sir.
sure. So okay, let me write the argument. So suppose this R and M has a GCD which is D, and D is not 1, so D is greater than 1. So if that happens, then this D is going to divide R as well as M. So it's going to divide Rx, and D also divides My. So D divides Rx and D divides My. So that being so, D should divide 1, which is not possible.
Yes, sir.
Because if it divides this and this, it should divide this as well, because one is written like that. So it is Rx minus My is equal to 1. So that is why GCD cannot be more than 1. It has to be 1. So, so is it okay?
Yes, sir.
Oh, fine. So, so we are now going in the other direction. So suppose R and M is 1. So the GCD is 1. Then there exist A and B. So I'm just claiming this. Okay, just change the color. So yeah. So so if the GCD is 1, then there exist A and B integers such that AR plus BM is equal to 1. So this is a fact I'm using. So we are going to discuss this in the tutorial. So it comes from Euclid's division algorithm, and we would use this to find an algorithm to for inverses. So given an element in a ZM, how do you find the inverse? How do you find the inverse of that? We will discuss that in the tutorial. So I'm not elaborating on this. So just remember this fact that if the GCD is 1, then there exist A and B integers such that this linear combination is 1. In fact, I should also mention that if the GCD is something else also, then you can write the GCD as a linear combination of these two elements. Oh, some line came from somewhere. Oh, so how did this line come? Okay. So yeah, it is gone. Yeah. Yeah. So we just assume this fact, which would be discussed in detail in tutorial. So using that, now let's reduce it modulo m. So this part is divisible by m. So this is 0 mod m. So AR is equivalent to 1 mod. Sorry, I should write 1 as just line here. Mod m. So this is 1 mod m. So that implies that R is invertible just by definition of it. So R is invertible. So that this part is also straightforward, of course, modulo this fact, which we would discuss. So that is our first theorem. And this also calls for the Euler phi function, which I would introduce now. So of course, I mean, all these things, many of you or maybe all of you are familiar with. So just recalling things essentially. So for an integer, just write like this, that for an integer m, phi m is usually called Euler's phi function or Euler's phi function. So this denotes the number of r integers less than equal to m, such that r and m uh, r and m is so they are co-prime. So the GCD is 1. So of course r cannot be m, so it goes up to m minus 1. Maybe I should just write 1 less than equal to r less than m. Yeah, it cannot be anyway m. So there's a number of integers between 1 and m which are co-prime to m. So it just count that, and that is phi of m. So it's usually called Euler's phi function. So by this above theorem, what we can say that these are precisely the elements which are invertible. So this is exactly the number of invertible invertible elements of Zm. Yeah. So that's precisely the statement of the previous the first theorem, that an element is invertible if and only if it is co-prime. So if I'm just counting the number of co-prime integers, then I'm just counting the invertible elements. It's just that the number has to match. The next theorem, so if R is invertible, invertible in Zm, then R to the phi of right like this, so same notation, R to the phi of m, R raised to the power of phi of m is congruent to 1 mod m. So how do I prove that? So let um denotes the set of all invertible elements. So let this be the set of all invertible elements. All, okay. Let's write be the set of invertible elements of ZA. And let's write as x1, x2. These are commas. Yeah, so sorry about that. So this is xk. So just make a list of all the invertible elements. So since the number of invertible elements is phi m, so k is phi m, where k is exactly p of m. That's the number of invertible elements. Okay, so I have to add which. Just a second. Which so yes. Mm, yeah. So um is the set of all invertible elements, and we have written the set as a list of elements x1 to xk, and so k is phi of m because that's the number of invertible elements, and for each xi, I is in this set. So so just if you pick any element from this set then xi times r is also in also in this set because if you multiply two elements, multiply two invertible elements, then you get an invertible element. I just remember that r is from this statement of the theorem. So r is an invertible element. So if you so r is an invertible element, and xi is another invertible element. So if you multiply them, they would you would still get an invertible element. So all these xi into r are elements are in this set xm, and they would all be distinct. So this you can also write it as rx1, Rx2 Rxk. So the same set you can write it in two ways. So one is just this x1, x2, xk, and then if you multiply by an invertible element r, then you are essentially permuting the set. So it's another permutation of the set. You are simply rearranging it. So you get the same set and another rearrangement of the same set. So therefore, so if you multiply all the elements together, so x1 into till xk, so if you just take the product of all of them and product of all of these elements, that should be same, because you are taking product of the elements of the same set. So if you, so the left hand side denotes the product when you write the set like this, and right hand side denotes the product of all the elements of when you write them like this. So these are just just an rearrangement, just a permutation of these k elements. So these two sides are same. And so what is let me just write that. So you have k copies of r, so this is r of r to the k, x1, x2, xk, and this x1, x2, xk being product of invertible element is also invertible. So you can say that rk is 1 mod m, and that is what we wanted to say, because k is phi of m. That proves the theorem. So if you have an invertible element r in Zm, then r to the phi m, Euler phi function, is 1 mod m. And this has a nice consequence. We can write it as a corollary. So when m is say prime, so say p, so p is a prime, then phi of p. So every element less than p.
P minus 1.
Yes, it is p minus 1. Absolutely. So every element less than p is co-prime to p, so it has to be p minus 1. And then if you take anything which is co-prime to p, that represents an invertible element, and n to the, so this theorem would imply that n to the p minus 1 is 1 modulo p. That's again very useful in various ways. So we would also see uses of this. Okay, so one small exercise using this. So let me write that down. So if n is an integer, show that n to the 5 and n has the same last digit as, sorry, digit in decimal expansion. So when you write the decimal expansion, they end up with the same digit. The last digit is the same. Same digit in decimal expansion. So that's a simple exercise to try. And I would also add some more exercises, but let's move on. Let's move on for the moment. Exercises we can discuss later. So yeah. So now we are sort of cleared out our notations about this Zm, this ring. And let's go to some combinatorial problem. So, so it is. It's called Latin square. So I would explain what it is. So, so historically, it probably it started much earlier, but this is the a famous incidence of this. So, this. So Euler posed a problem in 1782 that says that asks for this following, that arrange 36 army officers, so that is 6 square. So you have 6 square army officers. They belong to 6 ranks and 6 regiments, and arrange them. So the problem is to arrange them in a 6 cross 6 square such that each row and column contain each rank and regiment only once. So each row and column should contain, and yeah, I should have written exactly once. Yeah, so each row and column should contain each rank and regiment exactly once. So let's just start with an example rather than just do it like that. So let's start with an example, then it would be clear what I mean. Uh, so let's start with a smaller example. So let's take 9 officers. So of three ranks and 3 regiments. So suppose the ranks are A, B, and C, and regiments are alpha, beta, and gamma. So what we want to do is the following. So we arrange them by uh, rank first. So let's arrange the ranks. So arrange the ranks like this. I think I'll just use the same color I started with. So so I have to arrange it in a 3 cross 3 square. So arranging it like this: A, B, C, and then what I am doing, I'm just shifting one block to the right. So shifting one block to the right, I'll write it down later. So I'm just shifting one block to the right. So A comes here, so A comes here, B goes there, and then C comes back. So it's a cyclic process. So it just does like that. So now A goes here, so it pushes B here, and this is C. So this is just uh, what we should call one right shift. So let me write. So this is what we would call one right shift. So we shifted to the right. We shifted to the right by one block. So one right shift. And let's arrange the uh, regiments now. Regiments. So how do we? Yeah. So here we're doing something else. So we would shift one block to the left. So let me write that: alpha, beta, and gamma. So we are shifting one block to the left. Yeah. So so if I shift one block to the left, so gamma should come here and beta there. So one block to the left and alpha here. So gamma, then alpha, then beta. So that is one right shift with the same kind of notation, same kind of name. It is one left shift. Sorry. So shifting to the left by one block. Now let's put these two things together. So if you put these two things together, then A alpha, sorry, I would write this color first. So A, B, and C, C, A, B, B, C, A. And let's now put this thing. So just putting these two together. So alpha, beta, gamma, beta, gamma, alpha, gamma, alpha, beta. Now we have got a 3 cross 3 block. So we have a 3 cross 3 block, and each combination of rank and regiment appears only once. So each combination appeared only once, and every combination has appeared. So that is that's a so that solves Euler's problem. So that solves Euler problem for 9 officers. But Euler asked for 36. So that is 6 cross 6. So we have just solved the problem for 3 cross 3. So that's nice. So we would call these arrangements Latin squares. So we would see formal definition, but these arrangements are Latin squares. So here also see the just note that this A B C, these all three alphabets A B and C appeared in each row and each column, and they appeared exactly once in each row and exactly once in each column. So for example, this row has A, B, C, all three ones, and this row and also this row A, B, C. So every row and column has every alphabet once. And same for this. So these things are called these arrangements are called Latin squares. So we'll discuss that later informally. So just a little later. And so we have solved just now. We have solved the Euler's problem for 9 officers, but we have but Euler questions is for 6. So let's try another example. So another example. Let's try 4 cross 4. I think I have written it out. Just let me see. Yeah, yeah. So let's try the same thing. So what we have done, we have made one right shift to to the ranks, and one left shift to the other one, the regiments, and then punch them together. They've just put them together. So now let's do the same trick with 4. So try with 4 cross 4. Let's see what happens. So I have written it out so that it's a bit longish. So let me explain. So this is the first thing we are going to do is one right shift. So I have A, B, C, D now, and one right shift. So A moves to one block to the right. So this is the kind of movement happens. So this way it moves this way, and then D comes back. So it's just cyclic as it was in the 3 cross 3 case. And similarly, so all these are moving like this, one block to the right, and here we are moving one block to the left. uh, no, that is wrong. Just 1 second. No, no, no. Sorry, sorry. This is moving. 1 second. I just made some mistake. Mm.
So first row alpha, beta, gamma, delta.
Yeah, yeah, yeah. So just right. So yeah, yeah. So the fast row itself is wrong. Yes. So gamma and delta. Yes. Yeah. Then it matches. Yes. Thank you. So alpha, beta, gamma, delta. So and then we are shifting to the left. Yes. So to the left. So So again to the left, just the same thing happens. So this is one right shift, one left shift, and let's put them together. So we just put them together, just if just like the previous example with 3 cross 3, we put them together. But now we have problem. So problem is here. So this A alpha appears here as well as here. That's not allowed. And this kind of thing happens with many, because B delta and B beta appears there, here, and several such problems. So it doesn't solve the problem. So this doesn't solve Euler's problem for 4 cross 4, but that doesn't mean that 4 cross 4 doesn't have a solution, because this is one trick. This may not work, but there might be other tricks which would work. So so we would also try to understand this when this simple trick works. So I'll try to. So let me see if I have written something. Yeah. So let's. Yeah. So the first thing we're trying to understand is that when does this simple trick work? So let me. Yeah, some more examples. I'll just do it later. Okay, so let's go to a formal definition of Latin square. We start with formal definition of Latin square, and then come to this. So as I said, our first aim is to understand when does this technique work. This kind of cyclic movement works. So let me just go to the next slide. So so here is the formal definition. So you have A is a set of alphabet. So A is certain symbols, a collection of n symbols, could be numbers or alphabets. So so that I'm calling A. So A be an alphabet of size n. So alphabet means just symbols. So it could be numbers, or it could be English alphabet, or any alphabet would do. I mean, just any symbol would do. So then an n cross n array of alphabets of A is called a Latin square if each row and each column contains each element of A exactly once. That's what we have seen earlier. So what we have seen are examples of this, that each row and column. So we had this with A, B, C and A, B, C, D. So 3 cross 3 and 4 cross 4. And each alphabet appears in each column and row exactly once. Now there is some orthogonality relation which requires a definition. So if we take two such squares, L and M, so L is written, so both are n cross. Did I write? Yeah. So I have two n cross n squares, capital L and capital L, and their elements are written as small Lij and small mij. So they are Latin squares of size n. So they are n cross n squares on alphabets A and B. So A and B are certain set of symbols. So they are both n in numbers. So they are sets of cardinality n, some set of some symbols. So it could be numbers or alphabets, as I just said. Now these two Latin squares, so they are Latin squares. So they satisfy this property that each element, so each row and each column contain each element exactly once. So these two are Latin squares. Now we say that L and M are mutually orthogonal if every element of A cross B appears exactly once. In this if you just combine these two elements, so this is like taking product of this, so just combining these two. So if you make a list of all these elements, all these tuples, Lij and Mij, I and j running from 1 to n, both running from 1 to n. Then if each element of A cross B appear exactly once, then we call these two Latin squares are mutually orthogonal. I would give examples. In fact, examples are what we have just seen. So just let's try this 3 cross 3. So see what happens. So we have these two are Latin squares, obviously, because so on alphabet ABC. So this has alphabet ABC. This has alphabet alpha, beta, gamma, and both of them have this property that each alphabet appears exactly once in each row and each column. And when we put them together, then every combination appears exactly once. So there are 9 combinations. So alpha, beta, A, B, C, and alpha, beta, gamma. So there would be 9 combinations, and each combination appeared only once, exactly once. It appeared and appeared once. So, so these two are mutually orthogonal. So we say that these two squares, this ABC square and alpha, beta, gamma, these two squares are mutually orthogonal Latin squares. Here it is not. Here it is not, because when we put them together, we saw that elements are repeating and some elements are absent, certainly, because if some element repeats, then something has to be absent. So that is, so these two Latin squares, so they are Latin squares, but they are not mutually orthogonal. So Latin squares could be mutually orthogonal, they may not be mutually orthogonal also. So we saw both examples already. And just note that Euler's problem is to find a Latin 6 cross 6 Latin square, which, so two 6 cross 6 Latin square which are mutually orthogonal. I would explain that. So let's come to that. Okay, so I would write everything after this. Yes. And because the name is too long, mutually orthogonal Latin squares, so it is we would abbreviate it as MOLS. So Euler's problem. So just notice this, that just change color to emphasis. That note that Euler's problem is to find two MOLS, so mutually orthogonal Latin squares of order 6. So that is Euler's problem. So if you translate Euler's problem, so that's the translation of Euler's problem in this language, that we are trying to find two mutually orthogonal Latin squares of order 6. Now we have already we have already seen that we could solve this problem for 3 cross 3 using a simple technique of shifting this one left shift, one right shift. And we could not solve it for 4 cross 4. So there is a there is a theorem which says that we can do this in general. So that's not a surprising thing. It happens in general. So let me just write the theorem. So this movement to the left and to the right. So we have done one block, but we could have done multiple blocks. So you can move things to the left by multiple blocks and move things to the right by multiple blocks. These are called uh, circulant movements. So so this is circulant. So left circulant, and we call them, I mean, when you move it, so the square, what you the Latin square you get is called left circulant lattice square or right circulant lattice square. because it's a cyclic kind of movement, we would call that. So left circulant. So I'm not just better to just understand this practically than actually defining it. So it's a cyclic movement to the left or to the right. So it's either left circulant or right circulant. So the theorem says a left circulant Latin square and a right circulant Latin square are not mutually orthogonal if okay, Latin square of order n, I should say. Left circular lattice square and right circular lattice square of order n. So both order n of order n are not mutually orthogonal if n is even. So just remember that this process failed to produce this mutually orthogonal Latin square for n equal to 4, and this theorem says that that's not a particular case with 4. It happens whenever n is even. You cannot do this. You cannot get mutually orthogonal Latin squares by these uh, circulant transpositions. So let's prove that. It's surprisingly easy to prove. So, and we use modular arithmetic. So these are n cross n blocks and on n alphabet. So we would simply assume that they are elements of this Zn. So that can be done without loss of generality. So without loss of generality, we assume or just suppose that A equal to Zn, so written like 0, 1. So A is the alphabet, and both Latin squares have the same alphabet. Just assume that they have same alphabet, and yeah. So and also the first row is 0, 1. So first row is just this. So we can assume that. So we would assume that first row of both the Latin squares are exactly the same, and they are just 0 to n minus 1. So if they are not, you can always make this circulant movement to do this. So it doesn't matter. So yeah, so let's just notation. So now we have the first row. So what we do, so this is just the way we constructed those two Latin squares when we looked at this 3 cross 3 case. So we had this ABC and alpha, beta, gamma. So think of them as 0, 1, 2 and 0, 1, 2. Maybe I just explain that. I just go back to that. Yeah. So what I'm now doing, so I'm just taking A, just use some other color. So A is my Z3. So this kind of notations I'm using now. So 0, my brackets are very poor. So 0, 1, 2, and so I would write this as 0, 1, 2, and do the same movement. So 1, sorry, so 0, 1 and 2 comes here, and 0, 1, 2. So I'm just taking 0, 1, 2 and do the same movement. And here also the same. So this is 0, start with the same line, same arrangement, and then make this one left shift. So this is 1, 2, 0, 1, 2, 0, 2, 0, 1. So we do that, and if we put them together, then we have this 0, 0, 1, 1, 2, 2, 2, 1, 2, 1, 1, 2, 0, 2, 0, 2, 2, 0, then 1, 0, 0, 1. So each ordered pair appeared only once. So each ordered pair appeared only once and everything appeared. Of course, because we are just mimicking that. So that's the notation we are going to use. So that explains the notation. Uh, oh no, so this is something else. Yeah. Yeah. So without loss of generality, we consider the alphabet to be Zn, which is 0 to n minus 1, represented by this integers 0 to n minus 1. And first row is for both the squares assumed to be 0 to n minus 1. And then we do the the right circular movement and left circular movement. So let uh, L be the left circulant square. So and R be the just add a page. So L is left circulant, R is right circulant. Then the elements L, I, J is I plus J. So I leave this to you to check that this is L, I, J. The I, Jth element entry is I plus J. And Rij. So our convention is to write the Latin squares by capital letter and their entries by small letters with this suffix ing. So these are entries of this Latin squares, and this is j minus I. So now suppose that this n is even. So suppose n is equal to some 2k. then k and minus k are same modulo n, because their difference, which is 2k, that divides n. Sorry, n divides 2k, because n is exactly equal to 2k. So then k and minus k are congruent modulo n. That would imply that k plus j is equal to j minus k, because plus k minus k are same, so these two are equal. And if you look at these entries, then lkj is always equal to, so this is going to happen for all j. Whatever j is, these equality holds. And this is r k j. So these entries are always equal for all k, all j. So for all j, these two entries are equal, and that says that L and R are not mutually orthogonal. So that says that L and R are not orthogonal. So that's the statement we wanted to prove, that if n is even, then this trick doesn't work. So I'm not saying that. I mean, this theorem is not saying that it's not possible to find the mutually orthogonal Latin squares if n is even. It's simply saying that the technique of shifting to the left and shifting to the right won't work. So interestingly, this method works when n is odd. So if n is odd, so that's the next theorem. I'll probably not prove it now. Very similar proof. So just very similar proof. So this is going to work if n is odd. So a left circulant Latin square and right circulant Latin square are mutually orthogonal. Sorry. If n is odd. So this immediately solves the Euler problem for any odd n. So given any odd number, you can do just this simple trick of moving to the left and moving to the right and producing two Latin squares, and they would be mutually orthogonal. So you can just immediately, so you have two mutually orthogonal Latin squares. So you can immediately solve Euler's problem for every every odd number. So if you have to construct such, if you have to do the problem for 5 cross 5 with 25 officers of 5 ranks and 5 regiments, then you can do it. So I'm not proving this theorem. Maybe we can, I would probably include a proof when I send the notes. Yes, I would include a proof. That's better. So you can now easily solve for 5. So maybe that can be an exercise just to try that. So I'll leave some space for the proof, and I would again add some. Okay, so I can just write it here itself. So then, simple exercise is to so just writing like this: solve or construct two mutually orthogonal Latin square for of Latin square of order 5. So 5 cross 5. So that is just simple. So you can take 0 to 4 for the first row of both of them, and then do this right circulant movement, one right shift for one square and one left shift for the other square, and they would be orthogonal. You can put them together to solve this Euler's problem in that case. So Euler's problem is all but solved for every odd square. But even square, so even square is a little more complicated. So even for an even, we saw this. The previous theorem showed us that it's not this technique is not going to work. But that doesn't mean that there aren't. So we have to. Uh, yes. So next thing is. Yeah, so now we know how to construct two Latin squares, two mutually orthogonal Latin squares for odd order, for every odd order. The question is how many such mutually orthogonal Latin squares are possible. So that is answered by the next theorem. It's actually very easy. I would we'll talk about the proof. So there are okay, the maximum number. So there are at most n minus 1 Latin square, mutually orthogonal Latin squares of order n. So the maximal number of mutually orthogonal Latin squares of order n is n minus 1. So for example, for 5, if you want 5 cross 5 Latin squares which are mutually orthogonal, then you can get 4 of them, at most 4 of them. Yeah, so at most 4 of them. That's also important. But for 5, we will be able to construct all 4. So we will see that a little later. So why is this true? Proof is actually very easy. So maybe I would just write down a proof when I send the note. I can just talk about the proof now, so that's better. So we have this n, so alphabet of size n, and we again take, so the alphabet is Zn. So without loss of generality, we assume, and so this is represented by integers 0 to n minus 1. And we also we just start with this first row, and so 0 1 2 to n minus 1. Now what do we choose here? So these places. So suppose we have many such. I just wrote 2 such, so we have many such mutually orthogonal Latin squares. So what do we put here? So we can't have 0 here. So we can have so we have n minus 1 choices for this place. So we have, simply because we can't put 0. So we have n minus 1 choices. to fill this place. And that's the reason the maximal number is n minus 1. And for a given n, there may not exist n minus 1 many, it may be less. So in fact, that's a difficult problem. So so that is a question. So I write that question. So change color. What is the number of mutually orthogonal Latin square for a given n? So we know that there are n minus 1, at most n minus 1 Latin squares. Okay, so I should actually change this, is I would, otherwise that's a confusion. So the maximal number of this is less than equal to n minus 1. So it need not be n minus 1, but n minus 1 is the maximum possible. You cannot have more than that because you won't have choice of elements here. So you cannot have more than n minus 1. But do we have all of them for a given n? That's the question. So what is the number of mutually orthogonal Latin square for a given n? So Euler's in fact conjectured that, yeah, sorry. So Euler conjectured that. So yeah, you see, if you want to ask anything, just interrupt. So Euler conjectured that there are no mutually orthogonal Latin square. So you cannot get two mutually orthogonal Latin square. Okay, so MO, this is O, not the LS. So you cannot get two mutually orthogonal. There are no mutually orthogonal Latin squares for of order n, which is congruent to 2 mod 4. So if you take a 2 mod 4 integer, an integer which is 2 mod 4, so that is n is 2, is then it is 6, then 10, then what is the next one is 14, and so on. So just add 4 to all of them. So add 4 and it goes on. So 18, etc. So Euler conjectured that there are so conjectured that you don't have mutually orthogonal Latin squares for order n if n is 2 mod 4, namely if n is one of these numbers. So it also includes 6. So he said that his problem is it cannot be solved, and that is indeed the case. So for n equal to 6, there are no mutually orthogonal Latin squares. There are several proofs of this. Earliest proof was an explicit computation, explicit arrangements of all 6 cross 6, all possible 6 cross 6 Latin squares. but there are much more easier and elegant proofs available. So it is known that there are no two mutually orthogonal Latin square for n equal to 6. But if you just look at Euler's conjecture, so he says that it is not possible for infinitely many such, like whenever n is 2 mod 4, congruent to 2 mod 4. So that's an infinite sequence. But his conjecture was proved to be wrong by in 1960. Just mentioned that. Yeah. So in 1960, three mathematicians, Bosch, two of them are Indians, in fact, Parker, and just to get the spelling correct.
Srikande.
Yes, yes, yeah. Second. So they wrote two papers. One of them is Bosch Srikande and then Bosch Parker Srikande, and they established that Euler was wrong. Euler's conjecture is false. Euler's conjecture is false, and this mutually orthogonal Latin squares exists for any n greater than 6. Of course, for 6, it has been proved that there are no, Euler was correct only for 6. But beyond that, so you can always find it. And the construction is very complicated. So construction is complicated. So that yeah. So they in fact have an algorithm to construct such mutually orthogonal Latin squares, but that is complicated. So I would. So that much is the history. The next thing is what connects us to finite fields. So we have already seen that if n is even, then we have this trick of considering the one left shift and one right shift to produce two mutually orthogonal Latin squares. And the next theorem says, in fact, if n is of certain form, if n is a prime power, actually, we'll see that later, then you can find not only two mutually orthogonal, but you can find the entire set, the set of all n minus 1 mutually orthogonal. The full set exists, the maximum possible numbers exist, and you can construct them quite easily. So that's the theorem. Yeah, I'm hoping to be done with that in 10 minutes. So a complete set of n minus 1 mutually orthogonal Latin squares exist okay, so of order n, sorry, I should say order n first. Exists if there is a field of order n. So if there exists a field of order n, then you have a complete set of n minus 1 mutually orthogonal Latin squares. So if you are not familiar with field, then uh, just think that field has two binary operations, addition and multiplication, and you have multiplicative inverse for every non-zero element. So whichever is not an identity for addition has a multiplicative inverse. So we simply need to use this multiplicative inverse, that just this property to prove this. So let's see a proof. Yeah. So let F be a field of n elements, and we write them as a naught, a1 to an minus 1. So be a field of order n. And let L be its addition table. Just I'll just say what it is. So addition table. So like multiplication table, you can think of addition table. So you have addition operation. So this should be like just draw lines. Yeah. So I have this a naught, a1 to a n minus 1, and a naught, a1. So I'm just writing down a table for the addition. So this element is a naught plus, okay, I should just spread out a bit. So a naught, a1, a2, etc. So the first entry of this, so this is going to okay. So this last element is a n minus 1. Here it is wrong. So it is also a n minus 1. So first entry is just this addition. So a naught plus a naught. You can write it as 2 a naught. That's okay. Uh, and this is a naught plus a1. And so if you keep writing that, then you would get an n cross n block. So n cross n array. So that is L. So that's L. And now we construct mode Latin square. So that would be a Latin square. Uh, and what are the elements? So L is this. So L is this addition table. So if L is so L can be written in our notation small l ij, and the ijth entry is simply ai plus aj, the sum of the ith and jth element of the field. Now let L1 to be L, and Lk is defined as small lk ij. So define this. So this is defined, L1 is L and Lk is defined. So k is greater than equal to 2. And this is defined as Lijk is ai plus ak aj. Okay. Hmm. Okay, I just make a slight change. This is also going to work, but I would do this to stick to my notations. Yeah. And we also suppose that A naught is the additive identity. I should just mention it somewhere. Uh, so also suppose A naught is the additive identity and A1 is the multiplicative identity. Yeah, so we are doing this for, I'm sorry, this is 2 less than uh, 2 less than equal to k less than equal to n minus 1. So we have n minus 1 Latin square. So the L1 is L, just the addition table. And then we just manipulate the addition table slightly by defining the ijth element like this. We just multiply the ith element by the kth element and add it to the jth element. So that is what we have. So we have n minus 1 Latin squares. So we want to say that they are mutually orthogonal. So we take two of them and we want to say that they are mutually orthogonal. So let's suppose that it is not. So suppose, and then we arrive at a contradiction. So suppose LK1 and LK2 are not. Okay, I think I just need 2 to 3 minutes more. So it's almost time. Just are not orthogonal. Therefore, L so okay for some K1 K2 in this. So n minus 1. So suppose that we have two distinct squares which are not orthogonal, then LK1 IJ L LK2 IJ, this pair, so this pair should appear twice. So so some I prime and j prime. Suppose this happens, that I prime j prime. Yeah, so just putting this primes K2. So I'm simply saying that when we compose these two together, then the ijth entry and I prime j prime entry are same. So if that happens, then just use the definition. So ak ai mm, ak1 sorry ai plus aj is equal to ak1 ai prime plus aj prime, and the other one ak2 ai plus aj is ak2 ai prime plus aj prime. To add. So if you just solve these equations, then what you would get is just by subtracting them. So ak1, ak2, ai is equal to, just subtracted both sides. So ak1 ak2 ai prime. So if k1 is not equal to k2, that's the assumption, then ak1 is not equal to ak2. That implies ak1 minus ak2 is invertible. It's a field, so every non-zero element is invertible. And if we do that, since it's invertible, we can cancel it out from both sides. So cancellation holds, and so ai is ai prime. And this is also going to imply that aj is aj prime. Therefore, I is equal to I prime and j is equal to j prime. So these two places are actually the same. They cannot be distinct. So this is this is the ijth entry and I prime j prime entry. So these two are exactly the same places. So they are not different. This is I prime. Yeah. So they are mutually orthogonal. Yeah. So yeah. So if you so they are, so these two are mutually orthogonal. So they are four. So L1, sorry, L1 to L2 and Lk gives a complete set of Ln minus 1 is the complete set of complete set of MOLS, mutually orthogonal Latin squares of order n. So if we have a field of order n, then this happens. And in next lecture, we would see that this n has to be a power of a prime. So there are fields whose order is power of prime. So it's this way, that any finite field, the order of any finite field is power of a prime, or given any power of a prime, you have a field of that order. So you can just get this complete set of mutually orthogonal Latin squares of order n if n is a prime power. Now the question is, do we have such a complete set for other n's which are not prime powers? So that's an open question that is not known. So that is not known, and so we are now. So this leads us to the two finite fields. So fields with finitely many elements, and that would be the topic for next 3 lectures. So with that, I'll stop. So any question is welcome.
So I have a question.
Yeah,
so in this theorem, you have to prove L1, L2, L minus K is the only MOLS, right? But we proved that this set is a MOLS. But we have to prove that there is no any other.
Yeah, because the maximal possible number is n minus 1. So as soon as we
Okay.
cover the n minus 1 set, then it has to be the full set.
Okay. Okay.
Because we have proved that it's the n minus 1 is the maximal possible.
Okay. So suppose you are defining this L power k is you are multiplying this AK into AI.
Right.
Suppose you are saying that suppose you multiply with this AK to AJ, this also work, right?
Yes.
Therefore, this is different type of matrices.
Uh, yeah, but but it would be same. It will just give you a permutation of this. So if you write out the full set, then and change the operation, then it would give you. Whatever is the kth one entry here, that will be something else there, but the list will remain the same.
Okay, suppose you are defining like that. So we again we get some maybe we call some other letter L dash or maybe M. Okay.
Yeah.
Suppose we define some other.
So the proof is going to be exactly same. So if we just
again you get set again we get n minus 1 MOS. Both sets are equal, right? So this collection and this collection are.
Yeah. That's right.
So given any two MOLs, we can permute the columns. You get again MOLs, right?
Yeah. In fact, using this method, it's very easy to actually write down. So I was just trying to amuse myself by writing down some. It's rather easy to write down using this method. It's quite nice. So you can just I'm like for n equal to 5, you can write 4 squares with just doing this.
Okay. So is there any condition on this characteristic of the field?
Sorry,
that is there any condition on the prime? For any prime?
For any prime you can do. In fact, because there are fields which are, for every, as I said, that for every prime power there is a field of that order, and every field has order which is a power of a prime. So for any prime power you can do it. But of course, if you take prime powers, then those fields will be slightly more complicated. So writing would be a bit of an hassle. So like we would, next time we would start with examples of fields of order 9. So it would become a little bit of a complication to write those. But for primes, it's very easy because you can simply take this Zn. So if n is prime, then Zn itself is a field and then just write it out.
Yes, okay.
Yeah.
So instead of taking the additive table, can we take any other multiplication table or something else?
Okay. That's a good question. Yeah, that's a very good question. No, I haven't thought about that. So if you just start with multiplication table and do an additive shift. Okay. Yeah. That's a good question. I'll think about that. Yeah, I think it's a good point. So you start with multiplication. So we have multiplication at this point, but do an additive shift here. So write like AIAJ plus AK, that kind of thing. Yeah, so
No, you got to add this AK to one of these AJ, I think.
Yeah.
Because you are not multiplying AK to the addition. You are multiplying AK to the particular A in the previous definition. So maybe.
No, multiplying all three together. So because now your element is AIAJ.
So instead of multiplying this AK to AJ, you have to multiply AK to the sum of AJ, A and AJ. That is AK into AI plus AJ. Suppose you are defining like that. AK into AI plus AJ.
AK into AI plus AJ.
No, in the previous, the old one. L our K.
Okay.
Instead of defining this, if you define AK into AI plus AJ.
Okay, so here okay, so you are saying that you
Yeah.
start with additive addition table, but you multiply here with both.
Yeah.
Okay, so that we can quickly check if that works. So if we have that, so we'll have this kind of thing. Then we have K1 with this bracket here, K1, K. So it is going to have K1 here and K2 here. Yeah, so it will have K1 here, K1 here, K2 here, K2 here. So then if you subtract, that's becoming a bit complicated because
So we cannot directly subtract. You have to multiply some AJ, first equation, AJ to the second equation.
Yeah, so this is much simpler. Yeah, if you define like this, just multiply with one element, then it is the proof is much simpler, because I mean once you subtract, this part is gone. So AJ, these are just gone. So that makes it very easy. So essentially the elimination technique becomes easy if you multiply with one.
So, okay, instead of taking field, if you take some other division ring or.
Yeah, so that will be a problem. That will be a problem because
because we are using only the inverse property, not commutative property.
Yeah, true. Yeah, true. So, so division ring won't work. Sorry, division ring would work. Yes, division ring might work. But then, yeah, so what I mean is that if you have zero divisor, it's not going to work.
Yeah, that is okay.
Yeah, that's it.
Okay, sir.
Any other questions?
So I'm going to send this by tomorrow morning, along with the problems which we would discuss in tutorial on Sunday afternoon. And this thing, what I wanted to say. So, and if you solve some of this problem, and if you want to ask something, you can directly email me. That's a good option, or WhatsApp or email, whatever, because we are all in that WhatsApp group, so you can WhatsApp. I mean, if you have a question or a solution to a problem, you can, and you want to send it to me, then just take a picture and share it on WhatsApp. That's a good way, and that will be an easy way.
Okay, sir. Thank you.
Any other questions? Okay, sir. Thank you for your wonderful lecture, sir.
Thank you.
Okay, thank you, sir. The participants, the next lecture will be on 5/12/20. That is coming Saturday, 5:30 p.m. to 7 p.m. So thank you all for your presence. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you.